Welcome back to the Neuro Symbolic Channel. I'm Paulo Shakarian, and with me again is Peter Sutor from the University of Maryland and Simuli. And this is part 2 of our discussion on hyperdimensional computing. Peter, welcome back.
Good to be back.
Yeah, so last time, so if you're just seeing this video without having seen the first part, that'll be linked in the description and also at the end. We're not going to go over kind of the basics of hyperdimensional computing, the algebraic operations over the hypervectors and the base ideas of, why this stuff works. And today we're going to get into some applications of hyperdimensional computing, specifically along the lines of how to use hyperdimensional computing to manipulate input from a perceptual model or multiple perceptual models, such as a neural network. And for those of you who have tuned into this channel for a long time, you see that's kind of a running theme. We've talked a lot about metacognition, where you may have multiple models that you need to combine somehow. We've talked a lot about the interaction between vector representations and symbolic reasoning and things like logic tensor networks and logic neural networks in some of our past interviews. But hyperdimensional computing kind of brings a whole new way of looking at things. So without further ado, Peter, why don't you introduce us to some of the base concepts on how these two paradigms sort of can meet and what your research has shown?
Sure. Since a lot of this stuff is very visual, I think I'm going to just jump right into showing slides, if
sure.
people don't mind. Since we're on the topic of symbolic reasoning, so I'll start with this paper that we did on that idea of how do you do actually like symbolic representation and learning and reasoning with symbols using hypervectors. And if you recall, last time we talked about how do you do inference with hyperdimensional computing, and it looks sort of like this. And I'll add a little bit more detail to this before we talk about the symbolic reasoning, because I think that will set up how you would do that part here much more directly, I'd say. If you recall, I made this analogy before that there is a relationship between neural networks and hyperdimensional computing implicitly built in. Neural networks are sort of like quantum computing, where they're concerned with every single connection and how to backpropagate things and how to transfer signals forward and to other layers of the network. Whereas HDC is more like zooming out on this entire system and just observing the states of each neuron over time and modeling that as like policies, basically, like what is the grand pattern happening for each task that you're trying to solve. And then it expresses that as a rule. With the dimensions being big enough, the rules become possible to be constrained within that high dimensional space in a very natural way as noisy points around sort of the classes that you're trying to predict. So if you have perceptual data, it comes in as training examples, which under the algebra you can aggregate together and essentially find some superposed denoised version of the signal, and you XOR it with, in this case, a completely random vector representing some class, like dog, let's say. And the dog here is essentially a symbol just representing dog, whereas the training examples are the perceptual grounding of that dog in the real world. Now, what happens is XOR gives you a transfer, a digital transfer function from that perceptual space to the dog space, because XOR is the difference operator. So it's telling you what is the difference between the symbolic representation of dog and the perceptual signals coming in. And thus you get this sort of distributed model that's capable of approximately translating perception into an arbitrary symbol category.
And that's what's referred to as binding, right?
Yes, that's referred to as binding, yeah. And the superposition is referred to as bundling. And once again, once you have these models for each class, you can superpose the classes together, and you've got a distributed model that tries to reason on all those classes at once. And if you then have some perceptual signal come in, and you XOR with this big blue bar, which is the hypervector representing the entire model, it causes a superpositional collapse of the classes that don't align with this perceptual signal to become essentially random looking binary strings, while the ones that do have some relationship with it become much closer to zero, such as dog, let's say, would be much closer to zero than you expect, much closer to a zero vector. And that means that the Hamming distance between the XOR of the input and the model is equal to the dog class here, right? A noisy version of it. As you can see, I actually added some differences between the bits here just to make that clear. But it's so close to being that dog vector in that high dimensional space that there's like maybe a dozen to 2 dozen, maybe even 3 dozen standard deviations of significance towards that class, right? So you could be very, very certain that that's the correct class. So this is grounding perception into a symbolic reasoning system. Now, what the actual random vector represents here is just the brain's internal anchoring point of what that concept is, what a dog is as a symbolic thing. So it's translating it into some state of your brain that you associate with the concept of dog. And the idea would be that really, let's see if I have the slide here. Oh, maybe I don't. I had a nice slide somewhere where I showed different types of inputs coming in, all existing within the same large hyperdimensional space, but in their own sort of regions of that vast space, and all of them integrating together to describe this like anchor point of what a dog is. Maybe you heard a dog, or you saw a dog, or you smelled a dog, or whatever, right? All those things would eventually lead you back to identifying this dog vector. And as a result,
hey,
you
quick question on that. So when these types of models are designed based on these algebraic operations, are there results on, say, like the maximum capacity, like the number of classes, or or different types of things that could be stored in a single hypervector before you run into problems?
Yes, I actually have a graph that shows that. Maybe not on the slide, but if I actually open up the paper that I talked about last time, well, there's actually a formula that describes how that ability to identify things arose, and it's in the science robotics paper from last time, and it shows like what happens as you add more and more memories together of observations and try to suss out which memory is presented to you from the superposed memories. You can actually figure out which of these grouped together memories are presented to you from the average vector. If you give each of these examples an identity, meaning like you make an arbitrary vector representing the first thing, the second thing, the third thing that you added together, and so on, you can actually find the correct thing that you saw in the order that you saw it in, even by doing this. So much as you have a concept of first, second, third, blah, blah, that can be embedded into the aggregation part of this, and you can then also figure out which thing you saw first, which thing you saw second, which thing you saw third. That was a dog, for example.
Okay.
And the decay is basically it's essentially the coin flip problem, how it decays over multiple coin flips. So essentially, the significance of seeing something that you recognize erodes in this sort of logarithmic way towards the expected value of the XOR between two random strings, which is about half the Hamming distance, right? And so it'll get closer and closer to that until eventually it'll start getting false positives and false negatives because the variation in noise is enough to overcome that memory capacity at that point. So there is a limit at which you can start recognizing things precisely, but if there is a correlation between the input and output, it actually tends to reach this like steady state where it actually doesn't go further down. But if it were arbitrary information that doesn't actually correlate, like let's say you just make random vectors for everything, nothing's grounded perceptually, and you're just aggregating data together, then you will eventually lose resolution in that way. But if there is an actual correlation between the input and output, it reaches sort of like through a fixed point iteration to this like fixed template, this robust template that applies to all the observations you've seen. And at that point, it doesn't decay quite as drastically. And even though you might lose resolution on exactly which sample this is, you'll come up with like a second best guess that's very close, right? So it loses that property of precisely identifying, but it's essentially hallucinating things close enough to it at that point. So that's sort of how that gets described. And there's a formula that describes that, how that decays.
Yeah, but that formula in the Hamming distance you'll actually know if you're in that region, right?
Well,
versus like the precise or not.
Well, if there's no relationship, yeah, you can predict where it happens. If there's no correlation between the input and output, you can predict when that starts happening. If there is a correlation, it's tough to say when you've started like overstuffing that vector essentially with meaningless stuff. But you can sort of experimentally observe it by just seeing like how confident is it that this is the correct class? Like what was the difference between the first and second place? If that distance becomes too small, where you're worried that the natural variation you measure in the noise can like overcome that, then you know that you're towing the line at that point. So you want to be safely at least like a couple standard deviations away from random noise, right? So let's say you have a 10,000 bit vector, you expect a 5,000 bit Hamming distance between two random vectors. If you're 2 standard or 3 standard deviations away from that towards 0, which would be like 150 bits towards 0, then you're still good, right? You're going to be correct like 99% of the time or something like that, right? According to the normal distribution. But if it starts dropping below that, you start risking false positives and false negatives, basically. And that is a necessary problem for things within a set that are the same thing. It's more of a problem when you have different symbolic representations of classes and you're trying to predict the right one. So that's where it becomes an issue because you might predict the wrong class, right? But for like individual examples, it's essentially just hallucination at that point. On the global scale, it's more of a problem because you might predict the wrong class entirely.
Okay, yeah, that's really interesting stuff, especially since a lot of that, can be studied analytically, and
yeah,
the trade-offs can be examined, and you can make decisions on like, should I use a single hypervector for this one class and have like a different hypervector for each, or should I, bundle all the class bindings into a single hypervector? And I think that like those kind of decisions, I think, could be really intriguing in system design.
Right. Now, the reason I'm talking about all this is because of this approximately equal to part here. While your brain has an internal idea of what a dog is, it never actually recalls that specific random vector. It doesn't ever precisely recall it. It dances around it in some random distribution of noise away from it, right? With these observations. And the reason for that is because, well, you have to search through the classes to figure out which one it actually is. And so because it's not precise match, you have to search through your classes. And some people would often ask me, hey, okay, but like your brain doesn't search through like options in that way, right? So what is your analogy between like what a human brain is doing and what this is doing is sort of breaking down. But really, the way you want to think of it is this purple result here, which is not quite the symbolic vector, but is close, are essentially weights that get sent to things further downstream, which might, tell your muscles to move a certain way or your voice box to say something. And you might say to someone, hey, that's a dog, right? So really, the only reason we're searching through his classes is to communicate to another person what the model thinks it is. And we don't actually have to do that for the model to internally understand what it's looking at, right? That's internal to the model. It's for it to tell us what it's looking at. It has to search through those possibilities. And in a sufficiently sophisticated system, it wouldn't actually search through things. Those these embeddings that are noisy versions of dog would be sent to motor controls and then like turned into audio or like whatever that's transmitted back to the human observing the model, right? That's what the real pipeline would look like. The searching through the options is just for simplicity's sake for us to figure out what it thinks it is, right? So you can think of these as embeddings that would go further downstream to inform the rest of the model what to do in response to what it's seeing, right?
And so you could think of that embedding essentially as being like a PDF, something that captures like a PDF over the different classes and some other stuff that you might not know what it is. And maybe that could be handled better as input into something else. And we just use this matching with the classes as a way to understand the output as humans.
Exactly. So in other words, this output here is basically a neuro symbolic representation, purely. The specific identity vectors we chose would probably be chosen by the model at its own leisure, right? To try to tie it to the motor controls and what's trying to say and whatever. They wouldn't actually be random. But for us to impose it on the model as random is just for convenience to us as well. But yeah, it's a true neurosymbolic representation that then needs to be converted into a symbolic representation for someone else to understand what is being identified or reasoned on here, or what sort of reasoning is happening here. And so hypervectors have this ability to choose between being vectors and being symbols. Like you can collapse between one or the other at will from the algebraic perspective, and the system can set up whatever way it wants to do that, which is why hypervectors are part of a broader field called vector symbolic architectures, where you have some grand architecture that's using these vector embeddings and computations to come up with a result. Like, for example, word to vec or BERT, things like that are examples of that. You might not understand what algebra is underlying that system, but there is an algebra. It's just too difficult to express maybe from the system that you have, because the system wasn't designed to transmit to you the algebra. So it's sort of internally baked into it. Anyways, so for like my first foray into like how that symbolic representation works with hypervectors, I sort of thought to myself, well, what if you had a network that just returns to you some symbolic representation of what some sensory input should be? And to make that simple, I just took hashing networks, because it's very simple. They give you a nice short binary code, usually about 50 to 100 bits or so. And that code is supposed to tell you not only what that thing is, but also it has a rankability aspect to it, so you can rank different hashes to determine what the closest match for that actually is, right? And these are done through neural networks. I basically took 3 different attempts at hashing networks from the same authors. So they built upon their work and made better and better hashing networks. And I said, well, could you just like use all those hashing networks together at once, right? And so an example of how that pipeline might work: you have the training images come in, the pre-trained hash network has learned it or whatever, outcome short binary codes, right? You can arbitrarily project those short binary codes into a much bigger space. So we'll project it into a hyperdimensional space for the purpose of letting more examples from different networks of these combined together into bundles, basically. So you project them into a much bigger space to allow more things to be packed together through the binding and bundling. So for one network, you might aggregate these hash values for a particular class, let's say dog again, because why not build upon the same example here? And so you go through the same process of like identifying what this is from the hash code, building an inference layer for it. And once you do, you can, given an image, give it to the hash network, get a short code out, project that to a big space through the same projection procedure that you have. I think pretty much anything works there. You can repeat the signal over and over and then like randomly permute it to make it look random. You could randomly select bits from the 50 bits and populate a 10,000 bit vector that way, as long as you have the same distributional selection process. All of these are fine ways to project it into a bigger space. And then you can identify what the best matching class was from that, from essentially neurosymbolic labels from the hash network. But there's nothing stopping you from repeating that structure and giving each network its own identity through a random vector, and then smashing those together into one hypervector, whose sole goal is to identify something between these 10 classes or whatever, right? And what's fascinating is when we did this in the paper, there were 3 different networks. I believe DQN is the first attempt from the author, which got something like 60% performance or whatever. DCH was a Cauchy distance-based one, where they use like the Cauchy inequality to improve upon the result. And that might have gotten, let's say, like 65% or whatever. And then DTQ used triplet learning, and that was their best network, and it performed around, let's say, 70% on the data set. Well, it turns out if you merge them together, you suddenly get 77%. So you get a full 10% boost to your performance that you were missing out on by not including the other models. And the reason for that is because in this consensus system here, you pick and choose the best network for the task. So there are some things that DCH and DQN were better at than DTQ, that DTQ just had trouble learning as well. And so for those examples, DCH or DQN would take over the prediction pipeline because they just have a much bigger impact, much bigger vote in the consensus for that particular training example or test example.
So let me see if I can say this back to you. So you said with just using one hashing network, all you're doing there is you're essentially bundling the hyperdimensional representations of the sample with the class label and doing that to get your model. And so if I understand right here, where you have multiple, you're first for each individual sample, first you're binding the result of the model for that particular sample with a label for that model. And for the 3 models, now you're binding those labeled instances together. And now that's one sample, and you're binding all the samples, and then you're bundling all the samples and then binding with the class label?
No, so each of these already had those class label models trained. So each of these yellow vectors here have already existed. Essentially, they've been trained.
So it's the
you are
opposite
just taking
of what
them
I said.
Yeah, it's the opposite. You're just binding them with arbitrary symbols and then merging them together after the fact. And these, you can think of these as like layers. So basically, there was some layer before where these yellow vectors existed in 3 separate regions of the brain, let's say. And then as they get passed to the next layer, their origin point is sort of encoded into that signal that's being passed by the symbolic identifier. And then the next layer understands those symbolic identifiers and aggregates these, superposes those results together, right? And so it's like the next layer of the brain being informed by something from previous sections of the brain. And you can also think of the hashing networks themselves as being like sub-architectures of the brain transmitting some aspect of visual recognition to the next layers, right?
So what goes on is part of the input, since you know the model you're using, since you know each of the models from the input, it's essentially dividing up the problem into like 3 different classifiers almost, and leveraging the distance aspect of it to give you whichever one is most right based on the similarity.
Exactly. And that allows you to have multimodal feature representation. So the reason this is working better is because you have multiple modalities of features that look at different aspects of the data, right? There's nothing stopping you from making one of these like CNN features, for example, right? Or, stuff like that. Like you can add more and more modalities here, as long as they all get projected to the same dimensionality, right? They all exist in the same space, right? And they're all basically self-encoding systems within that space. And so you have this multimodal representation of your data that allows you to overcome that curse of dimensionality in the image space, because you're actually looking at low order sparse representations of that image in various ways, and then merging together those sparse representations to give you a robust view of what's going on in the image, insofar as what you're looking to do, which in this case is classify the image, right? And you can make these anything. Like you can make one of these like Fourier features. We could do like Fourier dropout and encode the sparse matrix there into hypervectors. That could be another modality. You could do the Laplacian of the Gaussian. You can do very simple methods of vision recognition here, but then you can also do very complicated ones like CNNs and stuff. And we'll see that in the next paper I'll talk about, where we do something like this with actual neural network embeddings, right? But this was sort of my first attempt at it, just to see how well the symbolic representations work. And my thought process was basically like these small binary codes that the hash networks provide are, I take them to be as like sparse representations of the image, which then I feel safe to project into a bigger space. But it turns out, I later found out that actually you don't even need that property. Even if the original origin space is very big, you can still project into a smaller hyperdimensional space, summarizing that bigger space. And you'll see how that works in the next one. But yeah, it turns out that this idea is more powerful than I originally thought. And once I looked more into the literature on HDC, I realized, hey, this is actually something that's pretty common to do in the field, and it just seems to work, like almost like magic sometimes, thanks to the algebra and the hyperdimensional aspect of it. So yeah, that paper, and then here are some results just so you can sort of see what's going on that might not be obvious from this under the hood. So I want to focus on the left graph here. This is essentially your accuracy on the task versus epochs of training. And what we did here is we basically, blue line is the original neural network. In this case, it's DQN, which I believe is the first simplest model that they had. And so after like nearly 2,000 iterations, it's at a measly like 15% accuracy or so. But while it was learning, we were at the same time observing the network's hash codes that it produced and learning a hyperdimensional version of that network. And it turns out the hyperdimensional version of the network figured out where the network was going to go way before the network actually got there. So its representations bootstrapped the learning of the DQN well in advance of the iterations. So I think this network will eventually, do this sigmoidal thing where it goes up to this yellow line and stops there. So around 65% accuracy or so, let's say. And the hypervectors got there with just a few epochs of training. They already sort of figured out what the algebraic representation that the network was going to come up with was going to be, what the rules the network was going to learn were going to be. And so this goes to show that the hypervectors are essentially learning the algebraic structure of what the neural network is doing, and they're trying to figure that out with these policies. And that implies that what the network does learn in the end is the algebra operating on the input space and the output space. So that's a very fascinating thing about that. And if you look on the right side here, what this graph is showing is basically the optimal Hamming distance for classification. With hashing networks, you have to basically empirically figure out what the optimal distance for discrimination is. So in this case, it'll clearly be 40, right? But with hypervectors, they actually don't care. It's any distance less than that bump works fine because it's ameliorated across the robustness of the superposition. So it doesn't actually care which distance you use. All the distances less than that distance are the correct matches, essentially. So these are very fascinating results, at least to me. I was very surprised by them when I first did this paper. Here's for another network. This is the Cauchy inequality. Interestingly, the Cauchy inequality one seems to do a lot better, probably because it assumes some sort of like Euclidean space already underneath it by the Cauchy inequality. So it's more consistent with what the hypervectors do. But even then, the hypervectors get to the optimal performance well before the DCH does. And lastly, this is their best performing network, the triplet learning one. Here, it's just insane. So within 50,
Wow.
well, actually within just like 10 iterations, the network is already at the 70% that the DTQ would get eventually. So it's actually insane how much it bootstrapped it for this. And I wonder why. I believe my hunch is that the triplet learning gives you like these policies much quicker, right? From very sparse observations, and so I think that's why you see such a drastic increase here. It's the discrete nature of what you're learning is much easier to pick up on for the hypervectors as discrete rules. But yeah, like this one in particular, I thought I must have made an error when I made this graph on the left, because like oh, maybe I just added a constant or something, right? No. It actually it was actually that drastic. And if he zoomed out over more epochs, what would happen is this blue line would like keep going up in these like step-like ways until it reaches the yellow line around 70%. So yeah, it's very, very interesting results for that paper, I must say. And it has some very serious implications about what's actually going on in neural networks when they're learning things. They're learning essentially policies under some kind of weird algebra that we don't understand because it's internal to the system and spread out across the layers and the calculations that the network does. But this implies that if you zoom out of the system and just look at like what each component is doing in a self-consistent space, like in one hyperdimensional space, these things can actually be constrained within one space and made very opaque through a simple algebra. And so that's what's happening here, is we've turned it into an algebra that humans understand, this binding and bundling algebra, basically. And as a result, it also gives nice properties for the network as well. So yeah, it seems like a win-win. Honestly, like everybody should be doing this on their output layer for their neural networks, I think. Like you can only get a boost in your results, I suspect. So yeah, so that was that paper on symbolic learning. Yeah, I think that's the last slide I have on that.
Next, let's talk about the gluing.
Yeah. Next, let's take this concept a bit further and just like use the raw embeddings from the neural network, which are of course a much higher dimensionality than the 50 to 100 bits of the hashes that are produced by the hashing networks. So this is a much bigger space. You know, let's say you have like a 300 component embedding, then those are 300. So let's say 16.
Is this all neurons, or just like, you know, the output layer before the softmax?
So in this case, it's the output layer right before the softmax. So basically, it's using the compressed representation the network came up with right before it's asked to predict the class. And you're basically hijacking that process and learning your own predictor in the hyperdimensional space instead of the softmax. So you're replacing the softmax here with whatever the hypervectors come up with. And, you know, one trick here was, well, how do you represent these embeddings in binary hypervectors? How do you, have like a range of values? So what we decided to go with was just a simple tanh transform on the embedding to normalize the values between -1 and 1. And so we were able to make quantized bins for that span of -1 to 1 based off of the empirics of the embedding. And those bins correlate to hypervector identifiers, which are then bound to the positions of the vector components. So each position in the embedding has its own symbolic representation. And so you can view this as a linear combination of the components of the vector, where each component is its own rotation in the subspace that you're like self-mapping to, right? Okay. Yeah, and that's that. And it turns out if you do the same exact thing we did in the symbolic hashing paper, it just works. This is just how we did the distance preserving quantization. We basically use something called gray codes, which gray codes attempt to make the transition function between binary vectors smooth, so that you don't have these jumps where instead of like one bit of change between two vectors. It's like all of a sudden all the bits change except for one, right? Which is usually how you see binary values represented. So instead, it'll smoothly transition, let's say, from the 0 vector, it'll, uptick one thing, and then one more, and then another one, and so on. And then, like you would, if you had to go further, let's say, then you would make this last number a 0. So again, you have a 1-bit difference from the previous thing, and you would go through the same pattern again, right? So you're sort of navigating, you're snaking your way through the hypercube. So that you're minimizing the number of changes in bits between each vertex. And that gives you smoother properties of the space, which makes it much easier than to turn into a hypervector. And these are just concatenated together, so they're not projected to the same hyperdimensional lengths that the hypervector, the end goal hypervector actually is. You're actually concatenating them together into one big vector to properly embed the semantic distance for each component of the embedding, right? And yeah, once you do that, you get a much better resolution. So here are basically heat maps representing how the typical way of doing hypervector-based linear combinations to represent embeddings looks. So there's two versions people stick to. One's called record-based, which is essentially doing like a inference layer, like what I showed earlier with the dog example, versus n-gram based decoding, which uses n-grams instead. And then a distance preserving quantization has a nice linear correlation going on instead, and you can see that the heat map is much more spread out in ordinals than the other ones. So this is much more informative for the hypervectors than what you start with. So that implies you want to take. What this is implying is the source for each of these numbers is like some sub-architecture of the brain that's smaller in its layer size of neurons than where you end up with in the next layer. So it's a bunch of small layers being projected into one big layer, right? So that's what's happening here. And yeah, a beautiful quantization effect on that. Now, what's interesting about hypervectors is because they're binary, and because you just have these simple algebras for manipulating them, you can actually learn multiple models on things that you got wrong, right? And then you can take those models that you got right and the models that you learned for the things you got wrong, and you can make one model that tries to handle both, right, in a structured way. And you can repeat this over and over to boost the efficiency, the accuracy of your model to the true optimum that you can actually pack in that vector.
So it's like XG boost or something like that. That kind of strategy. Yeah.
Yeah, and from a Hamming, from the field of Hamming codes and stuff like that, what you're doing here is essentially you're coming up with a better code, and error correcting codes are what that's called over there. And for the people familiar with the field of Hamming bounds, where they try to analyze the bounds on how many Hamming balls, so spheres of a certain Hamming distance, that you can pack into a space efficiently. That's what's happening here. So it's somehow trying to figure out a better packing of spheres into the space than what you originally start with. And yeah, so it's very simple. You have one model, let's say, get 76% of the things correct. You call that model A. You take the 24% of the things that got wrong and you train a model on that. That might get 70% of the things correct or whatever. You call that model B. And so now you can make a new model that is actually both of those models combined together. And then that model might get a better score than originally got. And then you can take its incorrect stuff and also, do that and so on and so forth until you don't improve anymore, basically. And if you're willing to actually have many models, not just 2 at a time that you smash together, but you have as many as you need to actually get perfect accuracy, you can, in a lot of cases, actually get perfect training results that don't cause you to overtrain on the output space, because these are superpositional. So whatever that you learn to achieve that perfect accuracy doesn't actually transfer to the test set if it doesn't transfer. Yeah.
So basically what you're saying is that, you know, it's not overfitting because there's this hierarchy of models and you're always starting with that first one that's likely more general, and it's only going up further if the first one is thought not to work, is thought to be in an error mode.
Yeah, exactly. Yep. Now, what would this look like in an actual brain? I suspect I would call these model B things that try to correct these errors. I would suspect those are the connections, the back connections in the brain that are basically going back and like correcting the signal that's coming in to be slightly different, so that downstream you can actually get the right result, right? So the brain has way more back connections than it has forward connections. I suspect they're doing something like this to essentially self-correct in many cycles until they reach this like fixed point in this process, which you can visualize this as like I present to you a picture, and if you could see the inside of your brain and how it's thinking, it might think this is first a dog or something, but then some microseconds pass by and you're like, wait, no, this isn't quite a dog, something's not right here. And then some more microseconds pass and you're like, wait, no, this is definitely not a dog, this is like some sort of weird chinchilla or something. Right? And so on until eventually identifies that it's not a dog, it's a chinchilla or whatever, right? So that process is being done by the back connections, and it's error correcting itself here, basically. So there's some error correcting pattern that you've learned over time, and it's running through that process through cycles of your brain, right? So that's what I think is happening here, as an analogy to the brain. But of course, you'd have to do real studies to see if that measures up to the theory here. But I think this is an interesting way to sort of get around this overfitting issue, right? So it's quite interesting in that process.
Yeah.
Yeah. And of course, hyperdimensional vectors are online learners. That's something I maybe haven't touched on too much here. So far what I've been showing is what's called static aggregation, where I make these models and then aggregate them together from the data and blah, 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 into a single model. And once the data has been, exhausted, that's it, I'm done with it, right? But there's nothing actually stopping you from the dynamic version, which is an online version where data comes in over time and you might form new models to handle the new data. And there's nothing stopping you from doing that here, because what you can do is when you do the superposition, really what's doing the learning here is the superposition. The only thing that causes learning is the actual addition part of the algebra. When you do superposition, you have counts, right? You have a count of how many ones you've seen across the components of the terms. And of course, then whatever is left over is the count of zeros. And you're choosing the bigger number between the two when you threshold the values into a single vector. So it's a 1 if you see more ones, it's a 0 if you see more zeros by the time you're asked to complete the sum. And it's if there's a tie, you add a random vector to break the tie, right? So if it's an even number of examples, you can just randomly make a tiebreaker.
So you've got to store, so then in that case, you got to store a vector of integers in addition to your hypervector to maintain those counts.
Well, I would say you don't even store the hypervector, you just store the integers. And, when you're asked to make a prediction, you threshold them at that moment, have them do a prediction, and then throw away that threshold of value and keep adding more examples to the counts. And if the numbers get too big in the integer, you can of course find the smallest count across all the terms, subtract that out as a static integer, right? And then the counts are essentially reset to a 0 point, and you can of course do this forever, as much memory as you have in your computer to store an integer of those counts, right? So it's essentially then an online learning, you can keep going. And there's also techniques for just saving a proper hypervector model when you're tired of making these counts and you're not seeing much variation because the numbers are too big. You can save that as a fixed model that you're going to run with because you haven't seen much changes over time on that model. And then you essentially have a cached memory. So you have a concept of old memory and then newer memory as a result. So an old model and a newer model. And you can have many such. So you can have like long-term memory, well, like gradual long-term memory systems that measure that. And I think that's a part of this field that hasn't really been studied yet. No, as far as I know, not many people have attempted to do something like that. But there's nothing stopping you from doing it here, right? So interesting things. If for the people interested in the results, we basically tested this on various things to see how HD glue measures up against other naive ways of like doing vector operations like KNN, linear SVM, RBF SVM, so on, log regression, Ada boost, naive Bayes, all these things. So we compared it to all of them, and consistently HD glue will beat these out, especially when there's very few examples to work with. So as you see, this is how many examples were presented to each of these before they were asked to make a prediction. And it's pretty consistent across that. And you can make the dimensions bigger for the hypervector or smaller and see like how that affects the system as well. It's quite common to use like somewhere between 2 and 16,000 bit vectors. So either 2 to whatever power is close to 2,000 or 2 to the power 14. One of those is basically what people like to choose for the task, and they figure out what the optimal size is for the optimal trade-off of efficiency and performance. Mm-hmm. But as you can see, it's quite reliably consistent in the static case. But and then this is for CFAR 10 as well, for the people interested in that. Now, I should talk about, I think, the results for this, for this one here. So what we did here is we used very similar neural networks. So these are all VGG11 networks, which have different hyperparameters. So they're the same network architecture, different hyperparameters. And what we saw is then you don't get that benefit of HDC as much because all these networks are too similar. There's nothing like interesting to squeeze out of each of them individually. They're roughly doing the same thing. Whereas if instead of all three of them being the same architecture, they were various architectures, you actually perform better. I don't know if I have a slide of that here in this presentation because this is when I presented the paper. Oh, I do. Okay, here we go. So you can see that that property flips on its head when you actually use different VGG models like 11, 13, 16, 19, and ResNet 18, ResNet 14. Suddenly the accuracy is better than other benchmark algorithms, or just as good. And so very interesting implications of this idea that you want very various disparate forms of modalities that have little overlap. That's the preferred way of doing the learning here. And for that, this is just more results. This is for CFAR 100. You see similar results there for that as well. So even for 100 classes, you still have these properties. So meaning that the number of classes is not really an issue here. And if it ever was an issue, you can make the classes hierarchical as well, like a hierarchical lookup of vectors that are randomly generated. And that can be pre-computed in advance to make sure you always get 100% recall. So in a dynamic case where you're learning online, none of the other models can really do that. So we couldn't really compare hypervectors to those models. But we did run the experiments anyway to see what happens. So in this example, we're basically starting out with, let's say, just 2 digits that are being learned, and you give each of them 100 examples. So for a total of 200 examples. And then you introduce 2 more digits where you have another 200 examples for each class. So those digits 0 and 1 actually have 200 examples each, right? Whereas digit 2 and 3 only have 100. And so on and so forth until you've introduced every class. And then the oldest classes have essentially seen 1,000 examples each. So digits 0 and 1 have seen 1,000 examples, whereas 2 and 3 have seen 900, and so on and so forth, where digit 8 and 9 have only seen 100. And you can see that it smoothly transitions into a completely new set of classes that I wasn't aware of. The decay is very smooth here. it's not catastrophically forgetting as much as like a neural network would if you try to do that with a neural network. So very good properties for an online learning system. And, you know, one thing I haven't mentioned is there's nothing ever stopping you from projecting to an even bigger hypervector length. So you can take a smaller hypervector and arbitrarily project it to a bigger length, either by repetition or random sampling into the bigger vector. And so, you know, if you find that the decay is unacceptable, you can actually like make the vectors bigger and bigger as you go on, right? Integrate more and more neurons into this process. And it'll have the same property here, but maybe with less of a decay in the performance as you go.
So that's kind of an interesting point, because, you know, one of the reasons that neural networks became so big was, you know, when I was in grad school, like, you know, this was circa 2008, like you know, always we talk about, like, we did logic, but we would use machine learning to like help us with the input. And always the discussion was, hey, you know, pretty much with any machine learning model, you can get to about 85%, you know, without a lot of work. And with a bunch of engineering, you could get to 90. And then there was not a lot you could do. This was pre-neural network. And then what neural networks taught us is that really easily, by adding more layers and more data, you can get very high accuracies.
Right.
What I think is interesting about what you said is, you know, maybe, you know, is it possible with HDC, by adding more dimensions, you get higher accuracies? And do you need anything else? And I think the other interesting thing is about adding more dimensions. It seems to me that that's easier to parallelize than adding more layers, which is kind of more the sequential piece of the neural network. Like, you're increasing the breadth as opposed to the depth.
Yes. Yeah. And, you know, I said that you could view the hypervector as like the state of the brain where each neuron has a label. Mm-hmm. But realistically, the brain has many layers that don't like in tandem update themselves. So actually can like update parts of the vector at a time, and precisely in the way you're saying. So you can either distribute like a one-step update, or you can integrate these like layers of abstraction and projecting into bigger spaces as you go, to update the rest of the neurons in these like cycles of propagating, you know, information through all the layers. There's not a lot of work that I'm aware of in looking at the vectors in that way. If you talk to a lot of people in HDC, if you ask them like about this issue, they would just say, well, just make the vectors bigger and it'll have the same effect. And actually, because the vectors are bigger, you have more representational power with that length. And so you don't really need more layers, you just need more neurons, essentially, is how they view it. But I do think that if you have the layers, this sort of like structure underlying the vector, where like you slowly update the vector until the whole vector is updated, might have better convergence properties. But it's also much harder to think about how you would implement that, and it's much harder to do. So I think it's a bit understudied as of now. So if anyone wants to, you know, look at new aspects of this problem, that's something to look into.
I think that would be an interesting direction, because it seems like a lot of what you talked about here and a lot of papers I've seen with HDC, it's kind of like, it's all about the HIL. It's like you just have some really good stuff to produce that HIL, and it does really well on some tasks.
Yeah, and I think if you properly did this like building on the layers, you can actually learn a whole network layer by layer, basically. So you can learn a hypervector representation for each layer, which might grow or shrink depending on what you need to do between each layer. That will essentially do like something like knowledge distillation on the original network into like a smaller, more compact, and more efficient hypervector network, right? So that's my ultimate dream. Like if I could like solve any problem in this field, I would solve knowledge distillation with hypervectors, because then you could take something like a transformer network and distill it into like a very efficient model that you can save and add more to over time, so you don't have to retrain, on the entire internet every time some new news articles pop up, right? So that would be, if I could solve any problem, it would be that. I think that would probably be huge if you could do knowledge distillation with hypervectors. And the difficulty with that, why you can't do it, is because knowledge distillation usually relies on like linking the loss functions and then back propagating the fixed network's loss function and like embedding information into the unfixed, still updating new network that's smaller. And so it sort of through osmosis causes the smaller network to appear like the bigger network to the best of its capabilities. But you don't have back propagation in hypervectors. So that's where the difficulty comes in. How do you actually do that? So you'd have to invent some substitute for back propagation, which I would surmise is very similar to this idea of error correction models. I think that's what it would look like. It would be more like the back connections in the brain than actual back propagation, because you don't have your closest thing to back propagation you have is the XOR itself, right? The XOR tells you the difference, and it's essentially like a gradient, insofar as you can get away with here. So that's the closest thing you have to a gradient with hypervectors, and this is like a nice way to actually incorporate that error into corrections upstream to get the desired result. So I think you'd have to use some form of this to do that. But yeah, I think that's pretty much all. Yeah, so if you're interested in the references, they're here offhand. So number 3 is the paper. Oh, I'm missing the I'm missing the HD glue paper here. Sorry about that. But yeah, the paper is literally called HD glue, so you'll probably find it if you just search HD glue.
Yeah, and we'll put links in the description for everyone. So, and just to wrap up, so this has been a great 2-part series. So thank you for taking the time, Peter.
No problem.
A lot of people that watch this channel will probably see this and want to grab some code and start implementing. What are some resources for for grabbing some code for HDC, and also what are some what would you recommend in terms of hardware platform for getting started? Because it's of course very different than some of the other paradigms out there.
So you could use what we used for most of these papers, which is a library made by my co-author, Anton Mitrokin, called PyHDC. So if you like Python, there's something called PyHDC that you could look up, and that'll efficiently handle hypervectors on any CPU architecture up to, I think, 8,192 bits. So it'll do that for you. If you want to go beyond that, you'll essentially have to make adjustments to that, because the reason it stops at 8,192 is that's just how many registers are in most computers that are up for grabs to like allow you to do like 1 clock cycle per hypervector operation, essentially, to most efficiently use your computer resources. And they do bit packing to make sure that you're not doing it bit by bit, so you're like doing only 1 byte with all zeros for the 1 at the end. Instead, it's like using all the bytes at once to do these computations. So you could use PyHDC, but there is a general resource for all hyperdimensional computing paradigms of source code and stuff that you can look up. And the name escapes me right now, but maybe I'll look it up and send it to you later. You could add it at the end of the video. But there is like some community effort to like aggregate all the links to source codes into one resource for people for all the types of hypervectors out there, because there's dozens of formulations of this, right? So this is just the binary one, which I think is the simplest one to work with for now, except for maybe Euclidean hypervectors. Yeah, I would say there's also a version of Torch, I think, that does hypervector operations. So I would look into that. There's a Torch implementation of hyperdimensional. I think it might just be called Torch HD or Torch HDC. So that will let you do a lot of things on parallelized hardware and GPUs, for example. Yeah, I think that's most of the resources I could think of that are out there. There's not too much, so feel free to add to the community on that. Like I said, not a lot of people work on this. At least at University of Maryland, I'm pretty much the only one explicitly working on HDC, although I think most people inadvertently use it in some way in neural networks. And there's only a few universities in the world that have HDC labs. I could think of San Jose, for example. UC San Jose has a really good HDC department. I think led by Tahana Rosing. I could be wrong about that. Tahana Rosing is who does a lot from that university in terms of HDC. And then Cardiff University has a lot of work on this as well, especially in spiking neural networks. So one thing I haven't brought up with hypervectors is the binary hypervectors are actually excellent for spiking neural networks. They're an excellent representation for spikes in spiking neural networks.
Yeah, makes sense.
Spikes together. Yeah. So there's new hardware generated to run spiking neural networks ultra efficiently, and I think that's done by the people at Cardiff in combination with IBM. I could be wrong with that, who they're exactly working with on that. So those are the two biggest ones I could think of groups that work on HDC. So yeah, there's not a lot of people, not a lot of resources. I urge people to use this as a tool and a tool belt. Add this to your lineup of tricks for machine learning or for even GoFi. Oh, one thing I didn't mention is this HDC is a great thing to add to any GoFi system, any good old-fashioned AI system that uses logic, because you can do fuzzy logic rules excellently with this, right? You can get around that brittleness of fuzzy logic or of pure logic with the fuzziness that's brought about by the actual hyperdimensional noise amelioration and superposition. So you can learn good logical shorthand rules in fuzzy ways that might get around some of the brittleness of GoFi systems. So that's another thing I've seen people use hypervectors in is fuzzy logic. Yeah, I think that I pretty much tapped out on.
No, this has been great, Peter. Thank you so much. And yeah, I mean, it's interesting you say that, because that was how I started getting interested in this. Was a paper presented at the NESI conference back in the fall. So,
Right.
But hey, thanks again. This has been really interesting. Really appreciate you taking the time for this two-part series. To everyone else, I will have some of these resources that I've been discussing with Peter posted in the description. Also, if you haven't watched part 1, please be sure to check that out as well. And don't forget to like and subscribe. Thank you so much.